So now we're going to see how we can apply those concepts and ideas that we saw previously uh, with TensorFlow and create networks to solve different kinds of problems. So I'm going to start to talk a bit about the graph mode on TensorFlow. And basically the idea here is that in TensorBoard we can examine the graph of computations for the model we are creating, and also look at some issues about numerical stability and the kinds of loss functions that we can use in TensorFlow. So when we actually try to implement something with those kinds of activation and loss functions we saw in the previous lecture. But mostly I'm going to focus on the exercises that you're going to do on the tutorial. We're going to have regression, predicting the miles per gallon based on the performance of the cars, the consumption of gas, based on features of the different cars. And also multi-class classification with this MNIST data set of handwritten digits. You're also going to do in the exercise binary classification using the fake banknotes, the real and fake banknotes data set, but that I'll leave that to you for the exercises. I'm going to focus a bit more on these ones. And I'm going to talk about TensorBoard too, because TensorBoard is a useful tool if you want to examine what is happening during training, your computation graph, and other statistics that you can use. It's often the case that TensorBoard is more a bother than a useful tool, because you need to write some extra code to send the reports to TensorBoard and so on. And if you're doing very simple things, it may not pay off to use TensorBoard. But if you're doing more complex jobs, then it may be a good idea, because it's a good interface to examine the training of your network. So let's start here with this with TensorBoard. This is a suite of tools for visualizing training and results, and you can even monitor your network during training with this. And it's written, this is a HTTP server that you start running, and it will monitor the log files that your program will be creating during training. So you can have the network training and keep track of what's happening looking at the graphs in TensorBoard. You can find more details in the programmer's guide in TensorFlow documentation. I'm just going to talk about this very briefly. And the idea here is that you create a folder where you're going to keep the logs for your model and during training. And TensorBoard will look at that folder and give you all the different logs that are there. And the convention is that each particular model or each particular run of a model should have its own folder. So in this case, we're going to create a folder called logs. This is the root folder. And then we're going to create inside of this folder folders called model something, and we can include here in this something a string that is always different when we run our code. So in this case, I'm using the datetime library to get a string with the current year, month, day, hour, minute, second. So this string will change every time I run the code, and it guarantees that I always have a different folder each time I run the code. The reason for this is that if you put everything in the same folder, then when you look at the charts, they will all be merged together in one single chart. If you put them in different folders, you can select each individual run and see how things are going. So this is just a suggestion of what you may do if you're using TensorBoard. You can start using this by default and then change depending on your preferences. But remember that if you don't put one run in each folder, then you see them all mixed together when you look at them with TensorBoard. So let's start, for example, with the logistic regression model and do a simple binary classification here. This is the same that we used last week. So we have the prediction here by doing the matrix multiplication of the weights and the inputs, and then we have we add the bias there. Here, if you want, you can convert the inputs to a tensor like we did last week. So this is just a sketch of the code. You can use the one you already have from last week's exercises, and then we compute the logistic loss, and we have here the gradient tape to get the gradients, which then we apply when training. So what we're going to do different now is we're going to create a log for examining with Tensorboard, but we're going to include there the complete computation graph for our model. That is this set of computations that we are tracking here for computing the gradient, which includes the prediction of the model and then the loss function. We want to represent all of this in one diagram so we can check all the different computations. And to do that, we're going to use Autograph. Autograph is implemented in TensorFlow to convert Python code into the computation graph with all the different tensors and operations and so on. So you can use Autograph to create the computation graph and then have TensorFlow execute the whole graph. That in that case you will not be using eager execution like we're using here. The default for TensorFlow 2.0 is eager execution, which means that when the interpreter is interpreting each line of code, TensorFlow is executing that part, those operations of that part of the graph. However, if you define the complete graph beforehand, TensorFlow can optimize execution by allocating different parts to different hardware. For example, some parts can be in the CPU, others in the GPU, and so on, and it can optimize execution better. We are not going to look at those uses of Autograph because we are not going to worry too much about the efficiency here and not work on very complex problems. But I'm just going to show you how you can do this here in the context of just visualizing the computation graph. So what we can do here is to use this decorator of TF function, and this TF function wrapper is what is going to track all the Python code, all the computations, and build the graph from there. So what we need to do is to just, inside this decorator, we can create a function that just creates the graph, and it receives the features and the label. And now it's going to call this grad function here. So what this function is going to do is to run all the graph that we have and compute the gradients and so on. But it's just a function that uses the complete computation graph from our model. And so if we run this function inside a function with this decorator, what TensorFlow will do is to store this computation graph. So it will create a computation graph and we can write it to the log. And the way to write this to the log, we need a log writer, a file writer object from TensorFlow. We can create one like this. So basically what I'm saying here is that I'm going to create a file writer to write logs to this folder. And this is the folder that I created that has a unique name for this run. So all the logs for this particular run will be in that folder. Now that I have this writer, I can call the function to write the graph. And what it's going to do is turn on the tracing on the summary for TensorFlow so that it can track the graph. And I'm going to create the graph. Note here that in this particular implementation, I omitted the parts here where I convert the input into a tensor and the labels into a tensor. So in this particular implementation, I am considering that I already received tensors. So you should do this because the graph should be only with tensors, and this way you avoid some strange problems that sometimes occur when we mix together NumPy and tensors and so on. So I'm doing this outside here. I'm converting everything into tensor, the labels and the features. And then I'm going to call this function, which is encapsulated here in this wrapper, so that TensorFlow can convert all the operations that are being executed here, and these include the predictions and the loss function. It will convert all of this into the computation graph. And since I turned on the tracing, the summary of the TensorFlow is keeping track of all these elements in the computation graph. So now I can export this trace, the graph that I created, to the log. And to do that, with TensorFlow 2.0, what you do is you set the writer that you have, that you want to use as the default writer by calling as default. And then in that context, you can call functions from this summary library to write things to that writer. So in theory, you could have different writers and write things to different logs if you wanted. In general, we're only going to have one writer and one file writer and write everything to that particular set of logs. Okay, so now we're going to start training here. One additional detail. Remember that last week we saw this problem with the predictions, where we used the reshape function to convert this matrix into an array, because otherwise when we were going to compare with the labels, we would get strange results if we were comparing a matrix with one column to an array of labels that was just a one-dimensional vector. One way of solving that problem, so an alternative to what we did last week, is to keep the labels as one column. So in this case, our labels are one two-dimensional matrix consisting of one column, and the prediction from our model is a two-dimensional matrix that consists of one column too. So when we're trying to match the two together, to compare them in the loss function, this will work. If you want to use your labels as just a simple array, a one-dimensional array, then you need to take care to reshape the output of the prediction or reshape something here in order that you can compare the two without having these errors. So there is no single solution that you need to use. You can use different approaches, but you need to be careful about the shapes of the tensors that you're comparing. If they don't match, then you can get errors in the result. So we take the labels. These are at the last column of our data. This is the same gene data that we saw last week. We take the features. They are the first two columns. We standardize the data and we create the file writer so that we can write the graph. And now if we write the graph, we can see it in the log. So basically, to use Tensorboard, these basic steps are: choose the name of the folder where you're going to store the logs. This should be different for each run, because if it's the same for all runs and you run your code several times, then the graphs will be a mess because it will interpret everything as being part of the same run. Then you create a file writer object for that particular folder, and whenever you want to write things there, you just set that writer as the default writer, and in that context call different functions that you have in this summary library to write different things to the log file. So in this case, to write the graph, we're using trace export, but there are different functions that you can use to write values and so on. Okay, so now we created the graph using autograph. This is implemented with that TF function wrapper, like we saw here. And this can be used for optimization and so on, and you can tweak lots of things when you use this kind of execution mode in TensorBoard, where you create the graph first and then have TensorBoard executed. But we will not be using that here. So this is something that has more to do with how fast the computation goes, and is not very interesting in the context of this course. So if you want, you can read more on the documentation, but here we'll only use autograph this time to create the computation graph, and just to show you how you can do this visualization on TensorBoard. Then, if you want to look at the visualization, what you do is in the shell prompt, so you can open a console, for example, on the folder where you have your folder with all the logs, so the where you can find easily the root folder for your logs, and then you just type logdir and the root folder where you keep all the different individual folders. So in this case, I created this logs subfolder, and in this folder I'm going to create several folders for all the runs. So this would be the root, the logdir that I have to give to TensorBoard, this logs folder, and TensorBoard will look inside that to see the different folders for all the different runs, and I can select them and examine them and so on. So this is what you get when you, if you run TensorBoard, it will run the server, and then you just open a browser on the local address, so the local host. This is 127.0.0.1, and the port is 6006. This one is easy to remember because it looks like Goog from Google. And if you point your browser there, you will see the interface for TensorBoard. So if you have several runs, you can select them here. You can select the charts, the graph, and so on. In this case, it was the graph that I implemented for this particular one, but then you can see them in the other architectures that you create. We'll see more examples here in this lecture. You can also add values to TensorBoard. So let's start the training loop. This is similar to what we did last time. We have this range, this loop for all the epochs. We shuffle our data. We create these batches by sampling from our data. And so in this case, what I'm doing is I'm creating the tensors for the slices in the features and in the labels. In the last week, what we did was to implement this inside the functions and just send them the NumPy arrays. But you can do this outside the function and send in the tensors. And in this case, it's better because this way we separate all the computation graph, which only uses tensors, from all of these conversions that we are going to move between NumPy and TensorFlow. And now we get the gradients, we apply the gradients with our optimizer, and so which I have I forgot to include here the code, but you have from last week. You need to create the standard, the stochastic gradient descent optimizer somewhere here, and then you apply the gradients. And now what we can add to visualize on TensorBoard is the loss function as we're training. So we're going to ask for the prediction here. We're going to compute the loss function from the prediction, and the prediction is for all our data. So in this case, we're going to convert all the data into a tensor. We're going to ask for the prediction, and we're going to print the result, or print the result in the console, but we're also going to write it into the log for visualizing on TensorBoard. So once again, we set our writer as default, and we write a scalar to the log with the name train loss. We give the value for that point, and we also give the step. The step is important because then Tensorboard can plot the variation of these values, and it will put one point at the corresponding step. So the step in this case is simply the epoch, so that we can see how the training loss is changing over the epochs. And then we can go to Tensorboard while our model is training and look at the graph, and you can actually see the graph appearing, and in this case we can see these problems here. So we have values here that are not a number, so we have some problem happening in our training. This is the loss function, and then it starts to getting not a number in the epoch. So this is one tricky thing when you're writing loss functions by yourself, because they may not be optimized for numerical stability. And the problem here is this one. We are taking the logarithm of predictions, and the predictions are the output of the sigmoid function. So this comes here from the prediction of our model, that is a neuron with a sigmoid activation. And if we look at these functions, the sigmoid is like this. For very negative numbers, it approximates 0 asymptotically. So in minus infinity, it will reach 0, but it's getting closer and closer and closer to 0. And the logarithm, as we get closer and closer to 0, it starts getting closer and closer to minus infinity. Now, if we take the logarithm of the sigmoid function, we should not easily get to minus infinity, because even though this starts to decrease very rapidly here, the sigmoid function will decrease very slowly towards 0 over on this part. So actually the logarithm of the sigmoid function should look something like this, and here be a straight line all the way to infinity. So there should not be a problem with this. However, since we are dealing with floating point numbers with limited precision, even a small rounding error somewhere around here could easily overflow this representation. So that's what we get this not a number here when we're trying to combine the sigmoid activation with the logarithm function. So there are solutions for this. For example, this solution by Mackler in 2012 was to compute the logarithm of the sigmoid activation in this way. If the value t that we input in the sigmoid is very low, so below minus 33.3, we just output the value t. So it's this linear part here that we presume is going always in the straight line forever. If it's below minus 33.3 and 18, we approximate by t minus the e raised to t, and then in the more reasonable values we use this other expression and so forth. So you see, we are computing this in different ways on different regions here to prevent numerical overflow. This is one example. In TensorFlow, it's this implementation here. So the maximum between x and 0 minus x multiplied by this z and so on, and the logarithm of the absolute value of x and so forth. So basically it's a different expression than what we're using here, just combining the logarithm and the sigmoid, that will give us the same result here, and then be more stable when we move away from 0. So what does this mean in practice? We don't really need to look at these details, but in practice it means that instead of computing the logistic loss like this for ourselves, we can use the cross entropy, sigmoid cross entropy with logits, which is this one here, but use it from the TensorFlow implementation. So what this function does is that instead of using the sigmoid activation value, it uses the logit, which is the the linear combination of inputs with the weights that is going to enter the sigmoid function. So what we want here is not the output of the prediction in this way. Sorry. So we don't want this output with the sigmoid function. We want this net value here. This is the log it that is going to input into that cross entropy function for that TensorBoard implements. So what we need to do here is we have this prediction function that returns the actual output of the last neuron, which is a sigmoid activation. But we're going to also create this logits function that does not use the sigmoid activation. So just returns this value that we compute here by multiplying the weights with the inputs and then adding the bias. And these are the logits that we're going to add input into this cross entropy function here. So now our logistic loss will be simply taking the output of the logits function here that I'm showing here. In this case, I'm reshaping into a single vector. Then I'm doing the same thing for the labels. So I'm receiving the labels for the classification and reshaping it into a single vector because this function is expecting that in this case. And now I am feeding this into the cross entropy function from TensorFlow and computing the average logistic loss in this case. So basically I'm doing the same thing, but I'm using this function instead of computing it manually like we did here because of numerical stability. So this expression here of trying to compute the logarithm of the sigmoid activation can get us into trouble with instability during training. Okay, so with this correction, now we just train everything. We need only to change a bit also the expression here when we are computing the loss value for the training set, because we changed those functions. We also need to change the grad function here, because now we want to use this combination of this function logit with this function for the logistic loss instead of going through the other one of the prediction. But after these changes, we fit everything together, and now we can see the training, and it works. So the idea here is that in some cases, due to numerical stability problems, you should use the functions provided by TensorFlow in the way they are provided. So in this particular case, this sigmoid cross entropy with logits needs as inputs not the actual prediction of your network with the sigmoid activation, but just that net value that we input into the sigmoid, because then this one will do everything in a more stable manner. And so in this case, we can get it to training, and we can follow the training in TensorBoard. So these are some loss functions that you already have. The mean squared error, you can use this one from TensorFlow. This one is not very problematic. If you compute the mean squared error yourself, it will give the same thing, because this one does not suffer from those stability problems. But this sigmoid cross entropy, softmax cross entropy, and so on, where you feed in these logits and it will compute on its own everything in a more stable manner. You should use these ones instead of implementing your own naively in the model. Okay, so let's see an example of a regression with a multi-layer perceptron. We want to predict the fuel consumption of cars. We have this auto miles per gallon data set that is taken from the UCI repository. And so I prepared this data. We only have numerical features in that table, so you can just load the data, shuffle the data before splitting into training and validation. So in this case, we're going to use a validation set to check if we are overfitting or not. Our target will be the first column, which is the miles per gallon that each type of car consumes. You should standardize the features and the target. You can leave the target as you have originally, but you can also standardize the target to avoid having a wide range of values, because in this case the target value is a continuous value and not class labels. So if you put it as with an average of 0 and plus or minus 1 or 1 standard deviation, so it's around 0, you can simplify then the problem of fine-tuning your network, training the network, and so on. We only have 392 examples, so we're going to use 300 for training and the rest for validation. The output of your network should be linear. That is, you should not put an activation function on the output, because you want to adjust to this continuous value in the regression. You should use the mean squared error loss function, because this is the maximum likelihood loss function when we assume that our predictions are affected by normally distributed random noise. And then you can try different activations in the hidden layers, different parameters for learning, like the rate and momentum, and experiment a bit. There is just one detail here. So in this case, I'm going to shuffle, standardize. I have the Y again, the target values as a column. If you want to put this as an array, just remember to reshape things appropriately in your code. And then the layer, this is one way you can use to build different layers. You can just create a function to create a layer. So I'm saying what is the shape or the inputs that I want to put into the layer, how many neurons I have, and the name of the layer. Actually, I'm not this one. I'm actually not using the layer name here, but you can use this for context when you are creating layers. To make the graph a bit prettier, you can group together different operations and give them a name. And I'll show you an example later on. But basically what I'm doing here is creating a set of weights that has it's a matrix with as many rows as the number of columns in the input. So remember that the rows are the different weights of the neurons, and we need as many rows as we have features in the input batch. And the features will be the columns in the matrix that has the examples. So I'm taking the number of columns in the inputs to be the same as the number of rows in my weights, and the number of columns in my weights is the number of neurons that was specified. And the bias vector will just be a set of zeros with this number of neurons. So I'm going to initialize the weights using a normal distribution here, using the random normal like we did last week, and set the bias at zeros. So this function basically allows me to create the weights and bias for a layer just by specifying what the input should be and the number of layers, the neurons I have. So now I can create this function to create a network, which is just a list of my tuples with the weights and the bias. So I'm going to create a list of all the variables by extending this tuple. So this means that when you use extend instead of append, it's going to append each of the elements. So in the end, I'm going to have a list of all the variables in my model, and the network will be a list of tuples with the weights and the bias together, which is more practical to do the computations. So now when I have this predict, I can for each tuple of weights and bias in my network, I can just do the matrix multiplication of the output of the previous layer multiplied by the weights, and the previous layer starts to be just the inputs, and then add the bias and activate with a leaky ReLU. So I'm going to do this for all the hidden layers until I reach the last layer. If you see, I'm starting with the inputs. I multiply the inputs with the weights of the first layer. I add the bias of the first layer, and then I set this net value, which initially had the inputs, will now be the output of the first layer. So when I go to the second layer, I am now taking the output of the first layer as the input into the second layer, and I keep doing this until I reach the one before last. Not the last layer, but the one before last. Because of all of these, in all of this, I'm going to use a leaky ReLU activation. Then when I reach the last layer, I'll just get the weights and bias for that one. I do the matrix multiplication of the output of the last hidden layer and the last layer that I have, the weights here. I add the bias, and then I just output this value without an activation function. Because I'm computing a regression, so I'm not using an activation function in the output of my network. Now, if I want to create a graph, I just call the predict here. So I'm actually creating the graph of my model without the loss function in this case. And I can now create write the graph. So the same thing as before, I turn on the trace for the summary, I create the graph, and then I write it to the log. So this way you can look at the graph of your model only looking at the model that you wrote. So in this case, I have here the multiplications, addition, multiplication, addition, and so on. And this would be one with 3 layers, and I'm looking at all the computations that I have in this prediction. Now we can use those names that I showed you before, because when you're doing the computation, we can add this scope to the graph by putting in a name for the layer. So in this case, for each layer that I'm computing, I'm creating this scope and saying that this is called layer, and then putting in the number of the layer. It starts as 1, and then I keep increasing that for the different layers. So now these operations in the computation graph will be grouped together under that name, and I can actually look at my model in this way, layer 1, layer 2, and output, because I called the last one output. And if I want, I can click on one of these boxes and look inside to see the details. So if you have a more complex model, you can name different parts, different groups of operations here and parts of the graph, so that when you are looking at the graph, you can see it at a higher level and then look down in detail on each of the parts. Okay, so here we're going to have numerical problems again. You can start by using a low learning rate, for example 0.005. I tried this one, and a momentum of 0.9 on the stochastic gradient descent optimizer. I used a batch of 32, and remember to use the quadratic error loss function and no activation on the output, because this is a regression. So the output here is just the raw value for the neuron, but you're going to have problems here again. And the reason for this is that we are now having several layers, and we can use many neurons here. So you can try, I don't have an example here, but I tried with something like 32 neurons in the first layer or something like that. And this can give you problems with the activation if you start with very large values for the weight. So then things start multiplying, and you can get very large numbers and overflow your values. So what you can do to solve that is here, when you initialize the weights, instead of just using a normal distribution with a standard deviation of 1, which is the default, which can give you fairly large weights, we can use a standard deviation of 1 divided by the number of neurons in the layer. So the more neurons you have in the layer, the closer to 0 will be the initial values of the weights, and this kind of evens out and solves a bit of those problems. But we'll see more about initialization strategies next week. This time is just for you to experiment a bit with these. Okay, so now you, when you are typing out, reporting the error, you should convert your error into miles per gallon. So to avoid, to minimize these numerical problems, we standardized all the data, including the target values, and we keep here the values of the standard deviations that we found for the original values in our data set. So now, if we want to convert this quadratic loss into a scale that is in miles per gallon, so we can understand the scale, you should take the square root of the loss, because the loss is the square of the error, and then multiply by the standard deviation of your original data, so that you move back to the same scale. So if you do this, you can look at the training error and the validation error in miles per gallon, and this gives you a fair idea of what is the error your network is making. So it should be fairly small, around 1 mile per gallon or 2 or something like this. You should get around there. Try different architectures, look at the training and validation errors. You can use Tensorboard for that, and try play a bit with the parameters to try to fine-tune this. So the other exercise will be to use softmax for multiclass, and we're going to use the MNIST dataset. To use this dataset, all you need to do is import Keras from TensorFlow. We're going to start looking at this further on, but we're going to use Keras right now because it's convenient to get the data. And so you can get the MNIST data from the Keras datasets MNIST. If you don't have this on your computer, it will download from the internet and store it locally, and then the next time you use it, it will simply use the local copy that you have. So you can use this load data function here to get the data, download it if necessary, and split this into training and testing, or in this case it will be training and testing. We'll keep these ones for test, or you can either split again this part, or you can just use these ones for validation and ignore the test. But in any case, the data already comes split into training and test. You'll have 50,000 images here and 10,000 images here. Now you need to reshape this so that, because these images are 28 by 28 pixels, and you need to reshape so that you have a matrix with 784 features and 1 example per row. But this is easy to do. You can do it like this. The images for validation would be, for example, the ones after 50,000. So you keep 50,000 for training, and then the others for validation here. These are 60, I think. I think these are the training images here are 60,000. So if you do it like this, you get 50,000 for training and 10,000 for validation. And the way to reshape is you simply reshape the images into a matrix that has as many rows as necessary and 28 times 28 columns, so that each image will fit into 1 row exactly. The labels. you just use the labels as they are. But since we are going to create this multi-class classification model, we need to encode the labels in this way, where, for example, if a point belongs to this class, then all the others are 0, and this one is 1, and all the others are 0. And this is what we'll have at the output of our network with softmax, which gives us the probabilities for each of the classes. So the labels are numbers from 0 to 9 in the data set, but you can use this utility from Keras to convert this into categories with one-hot encoding. So this is called one-hot encoding because it's a vector that has zeros everywhere, but a 1 in the position that we're trying to encode. So it only has a 1 and the rest is zeros. Do that with this function here so that you convert the labels on the data set that are integers between 0 and 9, and you convert them into these vectors that indicate which class each image belongs to with a 1, and the other classes it does not belong to with zeros. If you want in your predictions to find out which is the class that your network is predicting to have the highest probability, it's easy to use the argmax function from NumPy if you want to check that. Otherwise, just look at the loss function to see how things are going. So in this case, you're going to compare different activation functions in the hidden layers, sigmoid, ReLU, leaky ReLU, and so on. So remember that if you use sigmoid, expect that if you add several layers, you'll get a very slow training, so it probably won't work. You can try different network dimensions, different parameters for the stochastic gradient descent optimizer, and so on. And in this case, check for overfitting with the validation data. So when you are writing the loss function, for example, to Tensorboard or printing on the console, use both the training and validation sets so that you can follow your training and check if you are overfitting. Then you can even compare with different classifiers from NIST. If you want, you can go to that web page and check the performance of your classifier with those. So that you also have an additional data set that you can use, the one with the banknotes, and this is a binary classifier if you want to try that one, but I think that for the tutorials probably you'll only have time to do these two. Note that in this case today I'm only showing you parts of the code, and most of the code you'll have to figure out for yourself. So this is a bit harder than what we did last week. So to sum up, we saw how to use autograph to create the graph of computations. We are using this only to export to Tensorboard and look at our model, but you can use this in graph mode to have TensorFlow optimize the execution of your code. We also saw these problems of numerical stability and why it's a good idea to use the loss functions that are implemented in TensorFlow, and these two exercises, using a regression model to predict the miles per gallon of different cars, and using multi-class classification with softmax for MNIST. So look up what loss functions you should use, what activation functions, and so on. Experiment with the architectures and so. Okay, so now I'm going to log into Zoom and we can talk a bit, and then we move on to the tutorial part. See you soon.